All right, guys. So far we've done a couple lessons on intro to circuits. We've kind of looked how electricity flows within a circuit, and really the three things that you can measure. You can do more than just those three. The three things that we are going to measure in a circuit being voltage, being resistance, and amperage, or current. So now we're going to look at two different types of circuits that are. These are really the only two types of circuits that are used. All right. We're going to look at what's called a series circuit. This is what we've seen already. We've been dealing with this circuit the entire time, versus what's known as a parallel circuit, which is over here. Now, just at first glance, both of these circuits function pretty much the same, all right? On both of these, I close this switch, these two bulbs will turn on. Over here, if I close this switch, these two bulbs will turn on, all right? So what's the difference between the two? Well, it's actually quite a lot. And I'll tell you right now, almost every circuit in your car is wired this way as opposed to this way, all right? So one thing about a series circuit is there's only one path for electricity, all right? There's only one thing. So if anything breaks at anywhere in my circuit, I have an open circuit now, everything shuts down, all right? The other thing about a series circuit is pretend that these two bulbs, they're the exact same bulb, same manufacturer, same everything, all right? And I have 12 volts at my source, all right? Now, what will happen with those bulbs, since they're the exact same bulb, and I have two of them, as I'm taking my measurements, if I'm getting my meter out, all right, I got my meter out, I'm testing certain parts of my circuit, I expect 12 volts to be right here. So this is the power supply part of my circuit, all right? The fuse is not gonna use any voltage, maybe like 0.01, very little, if anything at all. The switch is not gonna use any voltage, all right? And so since I started with 12 volts here, I'm expecting 12 volts right here. Now, because I have a series circuit and I have two bulbs in that circuit, all right, it's gonna cut that in half. I'm gonna measure 12 volts right here. Assuming my switch was closed, I'll measure 12 volts right here and I'll measure 6 volts right here. Well, then for my next bulb, I'll measure 6 volts right here and 0 volts right here. All right, on a circuit, you're always on your ground path. When you're done, and we got our power supply here, we have our load, and then we have our ground path. On our ground path, it should always be 0 volts, all right? And so we're always gonna consume this. If for whatever reason, if I had 4 bulbs, all right, let's just do 3. I had 3 bulbs, all right? Again, I could expect if I was to measure these right here, and they're all the exact same bulb, all right? They're the same bulb all the way across. I'm gonna have 12 volts there, all right? And then let's see, that's gonna drop by 3, so I'm gonna have 9 volts here. I'll have 9 volts here. I'll have 6 volts here. Oh, no, it's gonna drop by 4, my bad. I'll have 8 volts here. I'll have 8 volts here, I'll have 4 volts here, 4 volts here, and I'll have 0 volts there. All right? And so it's just cutting it into a third every single time, all right? Because I have 3 lights there that are all the same lights, all right? And so let me go back to this original example though. Okay, so now, so it's going to use up all the voltage, and if it's the same component, it's going to be equally distributed to each component, and we'll talk more if it's not the same component, all right? Over here, I have a parallel circuit, all right? Parallel circuit. So this is a series circuit, and this is a parallel circuit. Now, when it comes to a parallel circuit, one thing that's two things. two things that really matter. All right, there's more than one path for electricity. There's more than one path for electricity. All right, now the benefit of that is if this bulb was to go out, all right, this branch of my circuit would no longer work, but this bulb would continue to work because I still have a path of electricity all the way around. So it can kind of isolate your issues a little bit, and you don't just lose complete functionality. You lose partial functionality, but you don't lose complete functionality. So that's a nice thing. The other thing about a parallel circuit is you're going to have 12 volts at each path. All right. So if I was to use this, I have my blue path down my power supply, going to here, and then going back to ground. All right. And then I have my green path. And then I'm going back to ground. All right. Once I close that switch, I'm actually going to have 12 volts right here and 12 volts right here. I'll have 0 volts right here and 0 volts right here on its way back to ground. So in this example, they function the same way. Hit a switch, 2 lights come on. Hit a switch, 2 lights come on. In this case, I'm getting 6 volts through each light. All right. We talked about current. And so I'm only pushing 6 volts through that. I'm only using my electrical pressure is only 6 volts. I'm only pushing so many amps now. All right. I'm actually going to have these lights will be dimmer. These ones over here, not only do you have multiple paths, so if something goes wrong, you don't just lose everything, but you also have 12 volts at each light. And so both of those are going to be brighter. All right. So that's a very, very important part. Now, it's also usually a little easier to identify an issue on this one. All right. You have a bulb out. I mean, more often the bulb doesn't work, it's the bulb, right? It's the most common thing. But if it's not the bulb, all right, if this bulb is out and this bulb is working, let's look at that. Let's look how that works. So if this bulb is out, but this bulb is working, my power supply side of my circuit is functioning because I'm getting power to this one, all right? That means that there's some problem between that connection and that connection, because I also know that my ground path is still working again because this side is working. So now I've isolated my problem to between these 2 points, all right, which obviously is much easier to troubleshoot. Now on the opposite side, if both are not working, that also shows me a lot of stuff. If they're both out, all right, that means I either have a problem, it's not in the load section of my circuit, all right, because both are out, they're wired in parallel. The only way I could lose both of those lights is if some part of my power supply is not working or some part of my ground path is not working, all right, and there's even ways we can check for that. So if you're not sure if it's on the power supply or the ground side, all right, and that's a hard. So we pull our fuse looks like it's going all right. All right, we turn our switch or, flip the switch. It feels like there's a contact in there. Sometimes that's hard to tell, but, it's probably easier to check other places in the car. If I have this switch closed, all right, if this switch is closed and it's not turning on, I can measure putting this lead right here, this guy right here, on the negative side of my battery. If I measure 12 volts there, and I measure 12 volts there, that means there's some problem with my ground path. Somewhere in this area right here, there's an issue, all right? The reason for that, all right, voltage is electrical pressure, so it's like the potential to push current. It can't actually move electrons unless there's a closed path. All right, the electrons are there. It's copper. We can get into the molecular breakdown of copper, but the reason why copper is a good conductor is because it has free electrons. It can actually, electrons can move across the molecules of a piece of copper. Where like something like a rubber, that can't do that, and therefore it does not conduct electricity. All right? So is what's happening here. I can measure here. If I have 12 volts here and I have 12 volts here, that means there's some problem with my ground path. All right? Because the only reason when you measure something, if I have a break right here, all right, I would go ahead and put my meter here. I'd measure here. I'd still have 12 volts, and I shouldn't have 12 volts, but I still have 12 volts there. All right? That means I could keep going down my line to find my break. Although then I check another spot down here and I say 0 volts. Okay, there's an issue between that last 12 volt reading and that 0 volt reading. Something's not working there. All right? Now, typically in most of your cars, like we have come off our battery and we go to a harness of some sort, all right, probably multiple harnesses. And then from there, it kind of branches out to every other part of your vehicle. So oftentimes in this scenario, I'll have a harness right here. All right. And so I can go ahead, and that's just it's the wire management. If you didn't have these harnesses, you'd have like a bird's nest of wires everywhere in your car. It would just be a disaster. So now I can come in here and check here. I can check on this side of the harness if I have 12 volts. Over here I have 0 volts. There's some problem with the harness, probably corrosion of some sort, or maybe just it broke and now you don't have a clean contact. All right. So in our vehicles, parallel wiring is used way more commonly. All right. It's because everything is ready to operate off 12 volts. It's made at the manufacturer, ready to run for 12 volts. Well, I can get 12 volts down each of my paths by doing it in parallel. If I have it in series, all right, you can't do that. You're actually going to have a voltage drop at each component. And so the third component on that path, well, they're all going to get, the third component may get less voltage than the first two or something like that. Now, on that voltage drop, let's say right here I had a fan, not a light bulb. I'll put F for fan. I don't know the symbol for fan. All right. I have a fan. And let's say a fan is going to draw more voltage. It requires more volts to go ahead and operate that circuit. Since these are not the same component, all right, it's not going to cut it in half. So the reason why it dropped from 12 volts to 6 volts and then from 6 volts to 0 volts is they were the exact same thing. So it just cut it in half perfectly. In this scenario, I may get 12 volts right here, all right, but down here, I may only have 4 volts left. This may have used 8 volts of my circuit because it has a higher resistance, all right? There's more resistance in a fan than there is in a light bulb. And so in this theoretical example, I can say, okay, I now have 4 volts right here, which means I have 4 volts right here, and I'll have 0 volts right here. So the reason I just want to point this out that it's not always an equal voltage drop going down the path, all right? It depends on the component. It's only equal if it's the same thing all along the line. Then it's an equal drop all the way down. Some things pull more, have higher resistance than others, and therefore you have a larger voltage drop. All right. Things like fans, electric motors, stuff like that are going to have a lot. Solenoid may have a lot, but then things like a light bulb, not so much. Okay. And then the last thing I want to show you over here is that within a parallel circuit, all I really have here is 2 series circuits. All right, it's just wired in a way where I can have more than one path for electricity, so I can maintain functionality. Even though something goes wrong, I don't lose my entire system. All right, so back on this example over here, let's say down this path, remember, at the branch, at this junction, I have 12 volts and 12 volts. I've not gone through a load yet. Therefore, I'm still on the power side of my circuit. All right. And so I'm expecting whatever my source voltage is to still be there because I haven't used any voltage yet. All right. But if I had a circuit like this, I would expect 12 volts right here and 0 volts right here. But if these were the exact same light, look at this. This circuit right here, if I cover up this side, it's the same as this circuit was before I put the fan in. All right? So I could expect 12 volts right here, 6, 6, and 0 on its way to ground. All right? So just to kind of give a quick recap. All right? Series circuit, one path, one thing goes wrong, whole thing dead. All right? Parallel circuit, more than one path. You can go off 10 more paths. All right? More than one path. Something dies or goes bad within that branch. All other branches are okay. If something goes bad from my power supply or my ground path, then they are all dead. All right? But that's good to know because that helps me identify faults. All right? And then really inside a parallel circuit, the rules of series circuit still apply. All right, a parallel circuit is just a more complex series. It's more series circuits on one path. All right, so that's not true, not more on one path, more on one power supply. All right, but then you break it out into multiple different paths. And you do that because you could spread that voltage across all those different paths. And so you have more voltage at each path. But once you go down that path, the same rules in terms of the voltage drop that you're going to see is the same on as you see right here. All right. And so that's why I still have 12 volts to start. All right. Because my power supply, I still have whatever my source voltage is, 12 volts. But they're still going to be dropping if there's more than one component on that path. It's still going to go by the rules along that path as a series circuit. I hope that made sense to you guys. Let me know if you have any questions and we'll work on it. All right, guys. Have a good rest of your day.